So today I will talk about the kind of the so-called comparison theorem. I'm trying to explain my results on the comparison theorem for perverse sheaves. So to explain the setting, so I first fix some notations which I use throughout this talk. So capital K always denotes the complete discrete variation field of characteristic 0. And little k is its residue field. And I assume that this is positive characteristic P and perfect. And as usual, O sub k denotes its ring of integers. And I consider a proper smooth scheme, okay, over OK. So here's OK. And Y, I avoid to write D because I sometimes use D for the modules and so on. So I write Y for the relative normal crossing divisor. On X. And U denotes its complement. And then in this setting, so we have a theory of Faltings on crystalline smooth, or sometimes it is called loose QP sheaves, which is a generalization of the notion of crystalline representation defined by Fontaine for Galois representation of the base. And he generalized to these relative settings. And also he defines the associated filtered. Sorry. Okay, filtered convergent F-isocrystals. And then he proves the so-called comparison theorem. Which is usually called C-crys or a crystalline conjecture. I didn't give the details here. And so I'm interested in, so the first, we can regard this correspondence. So this is in some sense a filtered Frobenius module with connections and filtered Frobenius modules with connections. And so this can be regarded as a kind of an analog of Riemann-Hilbert correspondence for varieties over the field of complex numbers. And over the complex numbers, maybe as everybody knows, we also have a correspondence for perverse sheaves and a certain D modules. And so I think it is natural to ask whether we have such a theory for this setting, in this p-adic setting. But on the other hand, so this crystalline is in some sense an analog of the unramified. In the étalic case, so it corresponds to the étalic sheaves, which is unramified along the special fiber. So if you try to understand in the étalic case, so then I think it's not so clear what is the perverse erratic sheaves which has unramified along the special fiber. So in my talk, so I just restrict myself to the case the perverse sheaves with stratifications define this normal crossing divisor. And also I have another difficulty is that because this theory basically relies on the Galois representation or finite étale site. And but on the other hand, for the theory of over complex numbers, so the correspondence is just by taking the solution complex or a drum complex, and so it's quite, the construction of the correspondence is quite simple, but for this case, we only have tools which is applicable to the Galois representation, so I decided to use a kind of descriptions of perverse sheaves in terms of certain nearby cycles associated to perverse sheaves, which is a locally constant sheaf on some log schemes of each strata. I will explain now. And also, yeah, such a description is actually is studied some years ago by, say, for in the erratic case, I think Bellinson and also some Verdier and so on. So was also in the overseas, so I think there is some studies in the also for this similar settings, that is with normal crossing divisors. Okay, so I also assume that y is so now I will explain how to construct this correspondence and also how to prove comparison. Okay, so I assume that y is a simple normal crossing divisor. So assume. And I also assume that K is absolutely unramified. And so then Y is the sum of the smooth irreducible scheme over OK. And I write its index set just lambda. And for the any subset of this index set, as usual, I just denote x sub I. I use I, not y. Yeah. So the intersection of yi. I allow the empty sets. So in the case of empty sets, this is just x itself. Okay, so then ui is just a complement of the smaller subscheme. I mean, the index. Yeah. So then we get the stratification. Thank you. Yeah. Okay. So this is the stratification. Okay. So then, as I said, I only consider the following category. So this is the category of perverse QP sheaves on the generic fiber of X with respect to this filtration, stratification, and such that. So then, so in this case, so the restriction of okay, so I give a name. on this perverse sheaves. So the restriction of the cohomology of F to its strata is locally constant sheaf or smooth sheaves, but and I assume that this has important local monodromy along the boundary. So in this case, y, no, so this is x, and so I is not containing I. Yes, thank you. So I should write k. Yeah, if I write k, so this is just a generic fiber. Thank you. So I did, yeah. Okay. Okay. So I also should say that in the theory of Faltings, he defined the notion of crystalline smooth QP sheaves, and if you restrict, and its local monodromy along the boundary, I mean along each component of y is unipotent if it is crystalline. So I think this is not a strong restriction, I hope. Okay, so now I will explain how one can describe these sheaves in terms of a kind of nearby cycles. So it's and to do it, I use logarithmic geometry or étale side of log scheme. So I write x log the x with the log structure in the sense of Fontaine and Illusi with defined by this normal crossing divisor. And if I write log for xi, so this is just xi with its inverse image log structure, so pullback of this log structure, so this one. And the same similarly for ui log. And so in this setting, so I have to give one remark that if you consider, so this is, if I write SM, this is a category of smooth sheaves. So then, so it is known that the category of smooth sheaves on this xi log is actually equivalent to this category. So the equivalence is just given by pullback and push forward. Okay. Yes, and I also should mention that this. Oh, okay. So I always work with Kumma et al. Topology. Yes. I used Ekedal's adic formalism. Yes. But in this case, just as the same as taking projective limit. Yeah, so this is just a sheaf. So maybe, yeah. But for the perverse sheaves, I use. Okay, so proposition is that if you are given perverse sheaves with unit potent monodromy, and I is the subset of the index set, and I sub I denotes the embedding of ui log into the total space. Maybe I should take the generic fiber. Yes. And then there exists smooth sheaf on this log scheme, such that the local cohomology of the pullback. I mean, so F is a sheaf on the scheme without log structure, but to define the nearby cycles, I restrict it to this one, to this log scheme, and then take a local cohomologies, and so you can prove that this is concentrated in one degree, in degree I. The degree, not degree I. So in degree, the cardinality of the I. Okay. Oh, excuse me. So yeah, so here I should remark that that. For here. Here I don't need. Oh, I don't need. Yeah, you're right. Yes. Okay, so furthermore, we have the map between them. So one is from phi I to phi I. And so I just, if you add one component which is not contained in I, then we have a natural map from here to here. And also we have a map in the opposite direction from -1. And so this satisfies. So here I take the logarithm of the local monodromy. So here I use unipotence. So the composition of CI-VI and VI-CI you're right. So just I am sorry. So okay. Thank you very much. So I should define the nearby cycle as so I can't correct so here. I'm sorry. I made a mistake. So I consider this in here. Yeah, because we have an equivalence of categories, so maybe we work. Yeah. Okay, so this is our log of local monodromy. And also we have something like Ci, Cj is Cj, Ci, etc. Excuse me. The other relations. So here's a Ci and Cj is equal to Cj and Ci. And also V, and also Ci and Vj. It commutes. C and V, composition of C and Vj is composition of Vj and Ci in us. Okay, so now, okay, so I think I will try to explain a little about how to construct this. So in the case n is equal to 1, so in this, I just explained in the case, the simplest case. So only one smooth component. So then we have this diagram like this. And then in this case, we only have C1 and V1. So in this case, so this is empty. So this is phi and this is empty. And so if you restrict this to y log, so this is just this one. So this I should explain something because so here is Rj lower star, but actually so this higher cohomology vanishes in this setting actually. And so then, so we have this isomorphism. And so, and then we have a map to, I should also restrict F to X log K. So maybe I should write K around here. Okay. And so then here's xk log twisted by 1. And so this is phi 1 f. So this is, so maybe, this is C1 and V1 is actually given by considering this map. R J prime. So I just pull back to UK and then push forward, and then we have a natural map from F to here. And so here, so I use I use unipotence of local monodromy. So then we get this one. Yeah, this is constructed like this. Okay. So then the first theorem, states that the functor, so I don't make it precise, but the functor associating F to, associating the nearby cycles to F, that is these data, is, I didn't give the target category, but target category is smooth sheaves on each stratum with C and V. Okay. And so using this, I define crystalline sheaves. So next I will explain crystalline sheaves. Yes. Not integral. Because if I don't take log, so then I don't. So since I work over over k, which is not algebraically closed, so I have to take log to get a map compatible with scalar action. So that's Okay, so now crystalline sheaves. So we have so then we can define also crystalline sheaves, crystalline smooth QP sheaves on this log scheme. So I forgot to say that this is not log smooth. So because we add log structure, so for the whole, I give a log structure given by the whole component of y. So this is not log smooth. So okay. So but anyway, we can define crystalline sheaves and also fully faithful functor to the filtered convergent F-isocrystals. Okay. So I just write the category of crystalline smooth sheaves with I denote it by subscript Chris. And so then, let me see. We have a map to MF nabla. I don't explain it in details, but this is, of course, this is a category of filtered convergent F-ice crystals. Since we work in the since we assume that the K is absolutely unramified, so we can interpret this as just a module with logarithmic connections. Yeah, with Frobenius. Okay, so, and also for nabla, I should be careful because here I consider xi log. So this is actually the isomorphic to this one. So, maybe I. So, yeah. So this module is big. Yeah. So this is not the differential module of the underlying schemes. Okay. So then I just define F is crystalline. So just a definition is that phi IF is crystalline for every I. So it's
what is the definition?
oh, which one?
It goes this way, if it went the other way, you take the image.
What?
So the definition of MF now, you just take modules with connection?
No. Just a module with connection and filtration Frobenius. Yes. Frobenius.
No, I'm just asking about just the crystals. You just take modules with connection in this sense? Or because the crystals, since it's not log smooth, the crystals are...
Yeah, you're right. Yeah, yes. I think one way is to give a kind of idealized. Yeah. So maybe I should hat, and so log should be smaller. Yeah. Please, I'm sorry. So. Hat is just excuse me. So just p-adic completion. Okay. No, not okay.
Does phi IF crystalline means what?
No. This is crystalline. What do you mean?
Oh, one can define it, and then there is a functor.
Okay. So and functor and I forgot to write here fully faithful functor. Yes.
You haven't given the definition.
I didn't. just maybe it's almost just parallel to the class. You have taken care of some so. No, this is just a full reference functor. So essentially, image is not, I don't know, even in the without I. Okay. Okay. So now, so just. Okay. Mm-hmm. No. Hmm? Oh. Faltings definition, yeah.
We can define.
Yeah. Hmm?
We're meant to imagine it's like that.
Yes. Okay, so now, so just also I don't I'm explain, but by gluing. So I just I don't explain here, but so just by gluing this the image of the nearby cycle under this under this functor. So we obtain a fully faithful functor like this to the crystalline sheaves to a similar category. So, but so this is the object is something like this, and I will just explain how this data looks like. So M is a coherent X hat D modules. So this is without log structures, and Fn M is a decreasing filtration compatible with. So this is not a D dagger. This is a usual D. And if we multiply Fn to Fm, so to have a filtration, we have to work with usual D. And to have a frobenius, we have to base change to the Berthel's D dagger. So the frobenius is something like this. Here's dagger. So I don't have much time, so I can't explain how to glue it. But so basically, it's just one can construct our functor explicitly. So really explicitly, using these data. Okay, so but I'd like to explain the comparison theorem, so I So the theorem is that for these crystalline sheaves, so the étale cohomology is crystalline. And exists a canonical isomorphism between this étale cohomology, so with the cohomology of this, the corresponding D modules. But actually, actually, I thought that I could prove the compatibility with all structures, but I noticed that so at some point I didn't check the compatibility with Frobenius because if you take the cohomology of this isomorphism, then you get the Frobenius of the cohomology. But I have to prove this theorem, I have to describe this cohomology in terms of certain complexes constructed from these data, that is decrease of the nearby cycles. And so I have to interpret this the Frobenius of the cohomology of the Dagger modules in terms of this one, and I didn't check it yet. But I expect that it's true. Okay. Now I will explain how to prove this comparison theorem. Oh. This is a drum complex. Without log. So here, we no log. Okay. So okay. Maybe. Oh. So to prove this theorem, I glue the cohomology using certain topos. So I will explain what kind of topos I use. Okay, so to do that, I have to introduce more notations. So J and I is a subset of the index set lambda, and xj is x with a log structure defined by I don't know which notation is the best one. So here I use the notation. J denotes that the log structure along the yj, where j is contained yj is removed when j is contained in this capital J. So so x empty is x log. So and x lambda is x with this notation. And xij is just the pullback of this log structure. Okay. Thank you. xi. And I introduced a category which includes the cohomology. So actually, I consider a fiber topos over a certain category. So the category is defined as follows. So I write it by B. So this is a category of pairs. Just I and J as above. And actually, this category is defined by the ordered set. So the home is consists of one element or empty set. So it's like this. And so if we have a map from ij to I prime j, then we have a map in the from between the log scheme. So xi prime j prime to xij in the opposite direction. So here I prime is bigger, so this is this scheme is the underlying. This scheme is a closed subscheme, and for the log structure, j prime is smaller. So here we add more log structure than this one. So we have a natural map between log schemes. Okay. So then I define the first the category. So this is okay. The topos. So this notation is not consistent. So maybe, but maybe okay. Anyway, I denote this by so not the site. So this is a topos of G, ij, tau f, and G, I, j is an object so of this étale. So I say that it's étale site, but here I mean étale topos. I'm sorry. So this is a topos. Yeah. And the second one is map between them. No. And plus so this satisfies cyclone condition. Right. Okay. Identity condition. Okay. So then we have a morphism of topos. Morphism of topos. And it is just defined by taking projective limit. So I have to also take up, I'm sorry, push forward. I forgot to take a push forward. Okay. Excuse me. Just a pullback. Yeah, just pullback. So this is just actually defined as just as a 5-out topos or 5-out site. So it's just usual projection functor. Okay. So this pi ij is just xij to the xk étale. Okay, so then I can define. So also, so this is for étale side, and I also defined a similar site for the D module. So this site is. It's just a map. Yeah. So it is important because what we construct is not an isomorphism. Yeah. It's similarly defined. But for this D module site, I use only this one. I don't add log structure on J because I usually, so for D module, I just work with coherent sheaves. I don't need to add log structure in here. So here, for this one, so x hat, I don't give a log structure to xi. And then for our crystalline perverse sheaves with QP coefficients, one can construct object in this category and CD. So what is D? D is a decrease of F, and dB of x hat B et, and its coefficients in K such that R theta star are CAs F, and CFIJ is smooth QP sheaves. And also so this is the drum complex of this one. And so we construct a comparison using this description, but so I will try to explain how this complex looks like when the divisor consists of only one component. So I will explain in the case n is equal to 1. So in this case, the index set consists of one component. So in this case, so yeah, we only consider the following three log scheme, right? So yes, and we have a projection and I. Okay, so now I would like to explain how to construct C of F and C of D in this simple case. And actually, I constructed this locally and then grew by simplicial arguments, so, but it's very complicated, so I just assume that. So I just give a local construction. So I assume that y is given by the equation x1 is equal to 0. So then we get using these coordinates, I can construct an extension of sheaves on y log k. And so then I just take a symmetric tensor. So this is a natural construction, but depends on x, y. Okay. So then f is constructed as follows. C of f is constructed as follows. So we construct a complex on here and here and here. Yeah. So okay, so in the left-hand side, so pi is this projection. So so I take R is sufficiently large. Yeah. And then, and also, yeah, Fi denotes phi I of F. Okay. So then, so it's very technical, but in here, in the left-hand side, we consider this complex like this. F1 plus R tensor C F empty restricted to y log. So it's the map is given by C. And so I think this is correct. And in the middle, I consider this without pi. But here I'm sorry, it is wrong. So here's this one. And so this one is a natural map, so I don't explain. But here is V. And on the generic fiber, this is just a complex like this. Yeah. Oh. And the generic fiber, this is, yeah, like this. Right? Yes. This one?
Yes, that sequence and the way you construct the higher things out of the sim of those things, it looks like the sequence used to construct the OX log things in mathematics. They able to do the complex related version of OX log.
Yes, yes. I'm not sure. I'm sorry. Okay, so this is something like this. So here we use C and V, and so the point is that we don't have directly glue these two. So maybe basically we like to glue sheaves on y and x log, but to glue these two, so it's better to insert y log in the middle, and then we can do it. So this is a point. And so similarly for the modules. So the module side, I will. So I didn't explain this map. So, but maybe I forgot. Yeah, it's a quite natural map. So maybe. So just define using this one. Yes. Or maybe take some logs. But I'm not. I'm sorry. I'm confused. So this is an extension. So here's x1. So we have a cohomology class in. If you just y log, yeah, right. So just considering a Kuma sequence, yeah. Yes, this is the x1 is contained in the log structure of y log. So we consider the Kuma sequence for log étale site, and so you get the element in here. So that this is a corresponding extension. Oh, yes. Okay, so now, so I also try to explain the D module side. So this is the C of F. It's something like this, and also C of D. So I will try to explain how this looks like. And so this is like this. But I don't explain the details, just how these two look similar. So here's the C d log x1, this. And in the middle, we have map like this. So yeah, I should say that we take the for this is just a complex. For this, I take the associated complex. This is a map. So maybe in that case, this is mapping fiber. Yes. And so here we have just a complex like this, and we have a map between them. It's something like this. And so this map is, this part is given by V. And similarly, we can't glue the complex only without Y log. So this V only exists only on Y log. So V is so we have to consider. But actually, so the middle one is the reduction of the right one. Just it's something like this. And so then, okay, maybe I should stop. But so I have to. Yeah. So the comparison map is constructed using. I give two remarks. One is about comparison maps. So this is just using use another site. So XB8. So this is constructed using the so-called Faltings site Yij associated to Yij. And also, actually, so on this site, so we have a natural map from this R to we have an exists and something like B Chris with connection T. What is T? T is in ZP of 1. T minus R B Chris with connections. B Chris with connections. So there are several kinds of B Chris. So this is B Chris with connections. So the B Chris with connection also depends on the choice of something. So we also, to obtain a global comparison, we have to work with some simplicial construction. Okay, so the next remark is that how to prove that this gives an isomorphism. So the comparison map is an isomorphism. So actually, so we work with unipotent, local monodromy is unipotent, and finally we reduce to the case, so isomorphism is just reduced to just the crystalline smooth sheaves on the component, by divisage. So because the local monodromy is unipotent, so if you just naively reduce, then we have to add log structure here. But the local monodromy is unipotent, so by just taking graded quotients, we finally reduce to the xik without log structures. And then I just actually the construction is not exactly the same as Faltings construction. So, but I check that his argument works in this comparison isomorphism. So that's completely the same. Okay, that's all.
Thank you. Are there comments or questions? Sasha.
Just a stupid question. Suppose that I want to define a category of nice QP sheaves on any algebraic variety, so that for points I will get potentially semi-stable Galois representations. And suppose that I would just define it directly by induction, by dimension, just saying that a sheaf on n-dimensional variety is good if a perverse sheaf, if all vanishing cycles with respect to all functions are good. So, so is it a absolutely stupid recipe for some reason?
So I don't know. So I'm sorry. So. Sorry. I'm sorry. That's wrong. So yeah. Yeah, you're right. So I should add a log structure without I component. So maybe I have to add a log structure along the intersection with other divisors. Yeah.
So this is the log smooth guy.
Yes, log smooth variety. Yes.
You could get rid of the other because they are just
Unipotence of the local. Yeah. But the unipotence. Yeah.
and then you apply something similar to.
Yeah. In the case of.
And so it's compatible with the research that
Yeah, because of course the comparison map is functorial, so just the visage. Yeah. Well, I don't understand. Of course, to do that, we work with Poincare duality and so on. Yes. Yes. I just follow the argument by Faltings. Yeah, he used it. Yeah.
Other questions? Okay, if none, we thank the speaker again.